like to introduce our special guest, Mr. John Walkup, Roger Key, yeah, from California State University's Fresno, CA, USA. The topic is about a shift toward scientific reasoning, the introductory Zion lab. So I'm sorry if my pronunciations of your names or title is wrong, so I'm sorry. So I would like to clarify that you have 1 hour and 30 minutes, or 15 minutes, sorry, for your workshop. So now I would like to give the time to our guest speakers. Thank you.
Thank you so much.
Yes, thank you very much. And your pronunciation of my name was fine. It was right on. Far better than what I normally get here in this country. Roger, do you have the PowerPoint up?
I do. Let me share it. Are you seeing the PowerPoint now?
I am.
Wonderful.
All right. So thank you, everybody. I'm John Walkup. I'm here with Roger Key. We're both members of the Department of Physics at California State University, Fresno. And what we're going to be covering in this session is a way to shift our laboratory, our science laboratory, toward scientific reasoning. And so we will proceed. Roger, why don't you go ahead and hit the second one? Okay, so we thought we would start off with a nice little survey. I'd like to know what the impressions are from the participants in our session here about how well do you think your students are prepared to conduct scientific experiments by the time they graduate. If you're a secondary school teacher, then you might think about what their ability to conduct science is by the time they graduate from that, from secondary school. And if you're a university professor, how do you think they're well prepared to conduct science for the careers that they are going to be engaging in? So few of the things that we want to take a look at, what about error analysis? Do you think that your students would understand how to analyze the error that they get in their measurements? What about statistics? Do you think that your students are prepared in terms of statistics like standard deviation and standard error and these other tools? And then also the scientific method, the way that we conduct science by forming hypotheses and performing observations and publishing and all that. How do you think that they are prepared? And so, Roger, why don't you go ahead and set us up with some breakout rooms? I'd like everybody to talk about this, and we'll come back in what, like 2 minutes?
All right.
Yeah. Okay.
Sounds good. Okay, here we go.
So before we do that, does anybody questions here about what they're being asked to talk about? Okay, so after a couple minutes, we'll come back and we'll generate some discussion about how students are prepared for being future scientists and engineers.
Okay, so John, I'm still working on how to get the breakout rooms going here.
Okay. Maybe we'll see.
Yeah, I've done it many times before, but I don't see the option right now.
I don't either. Maybe you have you been made co-host?
Yes.
That's really odd. I don't see it either.
I don't either. Could one of the hosts please help us out here?
Oh, okay, he's taking care of it.
That's good. Thank you.
Do you want to join into one of the breakout rooms, or should we just stay and let them talk?
Where we left it, we were looking at error analysis, statistics, and scientific method. However, I got the sense in the breakout room that many people here are teaching at younger students.
Okay. Well, the two that I spoke with were both high school secondary teachers.
Oh, well, that's good. Okay.
Okay.
So this is good for everybody.
Right, right. Especially when we get to the elusives, they're going to love those who teach the younger students are going to love that. Okay, so a couple of things that came out. One was that the students, they don't really feel that there's a huge gap between the skills needed to finish high school, secondary school, and to succeed at the university level. So that was one thing that came out. And the other one was writing. writing lab reports was also kind of a weakness that they kind of felt was an issue. What about you, Roger? Did you come up with anything?
No, I think the people in my session were either very shy or
I see.
teaching younger students.
Okay. You can, if you wish, anybody would like to type into the chat window comments they would like us to discuss, you can right now. And if not, we'll go ahead and proceed on with the rest of the presentation.
Let's go on to the next slide.
Okay. And then I'll notice if there's somebody's typing something in. Okay, Roger, this one's yours.
Okay. So one of the things we're looking at very closely here in our environment is addressing STEM retention through scientific thought and methods. So we are really striving to instill a sense of scientific curiosity in our students, whether they be algebra based or even less through engineering disciplines. And John and I attended a meeting not too long ago, and we met with Dr. Koenig from University of Cincinnati, and they were also moving in this direction. So we kind of formed a team and worked together for a while. And you can see here that according to our own statistics, 42% of students enrolled in our College of Science and Math leave college after the freshman year. That means after their first year. They are very discouraged and they leave after their first year. That's not good. 32% of biology, chemistry, and physics students fail to pass their course on the first attempt. And that's very sad. It means that we're not giving them the support they need. Many incoming STEM majors are underprepared in content and cognitive abilities and struggle through their introductory courses. So we're really working hard on getting them prepared well before we let them into those first tier classes. And 40% of the STEM majors report inadequate high school preparation as a problem in their current coursework. So that's a big focus for us right now. I'm working on several fronts to improve the teaching of high school science. And I feel it really comes way before that. It comes around when the students are at 10 or 11 or 12 years old. It comes when they are open-minded and really ready to learn, and they're not embarrassed to be wrong in front of their peers, because we should all be able to say, I don't know, but I can find out. It's an important thing to be able to say, I don't know. It's not a loss of face. It's not a loss of prestige or anything if you are not expected to know everything when you walk in. And then these are all coming from research targeting, of course, U.S. student populations. We've got a real problem here. We're working on it. And that's part of why we're presenting here. Hey, John, you want the next slide?
Sure. Okay, so what we decided to do was completely rethink the lab curriculum. And one of the standards of lab instruction that has been around forever, the traditional way of treating the lab, is to verify that which was learned in lecture. So if you have been taught that the acceleration constant for gravity is 9.8 meters per second squared, we set up a lab for students to verify that fact. However, that's not really tied to real world science and engineering. And in the real world, you rarely have a target value that you're trying to reach. Instead, you receive a result, and when you hit your result, success is going to be determined by how much confidence you have in your results. And that comes to error analysis. And so we started turning things around. We increased the emphasis on industrial statistics. So real world statistics, keeping in mind we're not bringing in some of the high level stuff, but at least we're lining it to the type of statistics that a real scientist and engineer would likely encounter. We're also teaching students now how to design the labs. So when we talk about this, what we mean is, for example, when you are designing to reduce the error in a lab, what kind of things can you do? If you're trying to estimate the mass of an unknown object, what kind of experiments can you perform, and how do you design those experiments? And so instead of having a cookbook where they just walk through a list of steps that carries them through the actual experiment, they design the steps themselves. And then, of course, the instruction we give them is designed to get them there by the end of the semester. Heightened algebraic manipulation, we stress that we want them to express an unknown in terms of measurable quantities, which means they must do more algebra than they are accustomed to in traditional labs. And then what I really like is our incremental learning objectives. So every one of our labs has a little matrix like this. And in this matrix, there are two parts to it. One is the new things that they're going to learn, and also what this lab is going to reinforce that they have learned in previous laboratory experiments. So for example, this is one that we pulled from one of our activities. In this lab, they under communication, students are going to focus on writing captions for figures and tables. That is the extent of their writing instruction for this lab. The next lab will focus on something else. But one of the issues that I have with the writing of laboratory reports is students have never really been taught how to do it. We sort of always assume that the teacher in the previous year has addressed that. And so what we do is we just assign them the report, and then we get upset when the reports come in and they're not very good, but nobody's ever taught them how to actually do these things. How often has anybody ever sat down with a student and said, here's how you write a figure caption. Now, we're going to have you write the caption for the figure, and then we're going to grade that. And what the nice thing about this approach is it also cuts down on your grading load, because now you're not grading a full lab report every week. You're only grading a part of a lab report, because that gives you an opportunity to really focus on the actual writing itself, and did they meet the elements of a figure caption. And so we have experimental skills that we want them to learn. In this case here, they're going to be learning confidence intervals in statistics, and the plan, do, check, act cycle used in industrial quality control. And then there's some soft skills that they're also going to learn, something about like quality control and data-driven decision-making. And these things sound real lofty. However, I think you'll see that these are actually quite attainable at below the university level. And I have a question here. Oh, I'm sorry, it's not. Okay, we're good. Roger, anything else on that would you like to talk about? Because I know you like this matrix a lot.
I do. I really like this matrix. This is such a versatile thing, and it needs to be included in all of our activities, but we have not yet achieved that. We're working on that. Mm-hmm. Because it strengthens and it reviews things that you've done before, and then things that you're going to do. And it's almost like that rule of making presentations where you tell people what you're going to say, you say it, and then you tell people what you said.
Right. And this also is unlike the traditional lab, because in the traditional lab, we try to get students to do all these things in their first experiment and then in every experiment, and they become overwhelmed. Rather, each week they pick up a new skill, and we're going to focus on that skill. And the other issue is the physics and the science becomes the vehicle for teaching scientific experiment, not the other way around. Okay, go ahead.
It's getting away from that verification style model of doing labs in physics. Okay, so these are some of the labs we've done, and we think are worth mentioning here. First is this activity on pulsars. Mm-hmm. John, you want to do this one?
Yeah, sure. Okay, so those of you may not be familiar with pulsars, but they start as neutron stars and then they shrink down. And because of conservation of angular momentum, as the star gets smaller, it has to spin faster. And these are stars that spin so fast that they turn the amount of time it takes to rotate once could be on the order of a millisecond. So they really, really rotate rapidly. But what's interesting about the pulsar is that it sends out bursts, sends out a constant stream of radiation out of its magnetic poles. So this thing acts like a lighthouse. It turns around and it whips around, and when the beacon, this beam of radiation hits the earth, you can detect it. And so what you end up with is this pulsing, and that's how they discovered the pulsar, because they got this pulsing from outer space that they first thought was actually aliens. And for a while there, they thought it was man-made, or not man-made, but some sort of intelligent being. But now we know that it's from a rotating object. And I lost the presentation.
It's coming back now. I just reshared with the sound.
Okay. Oh, good, good. Yeah. So the radiation pulses can actually be mapped to sound so we can hear them. And go ahead and play the pulsar, and we can hear the sound of it. You hear this? Chick, 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 chick. Okay. So the question now becomes, if you can find the time it takes between pulses, you can identify the pulsar. And the reason why is this, go ahead to the next slide. I think it's on the next slide there. Oh, okay. And so we have an activity here lined up, and that is, if you're going to identify the pulsar by measuring the time it takes between each of these pulses, what can you do to make these measurements as good as you can? And you know, we'll open that up. We'll have a little breakout room. But if I gave you that job and I said, look, it's really important that I know how much time is between each of those pulses, you know, and this thing is going chick, 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 like that, how would you go about making the best measurements you can? And so then we go into our breakout rooms for just a couple of minutes. And Roger, I think we best not go into the breakout room. I think it'd be better if they talk without us being there.
Okay, so let's leave it here and open the general chat.
Okay.
So I'm watching the chat. I think you are too.
I'm not watching the chat. I don't know what that means.
No, I have the chat.
Oh, the chat. I'm sorry, that. Okay.
Yeah.
Let admin send all presentations to Telegram group. I'm not sure what I mean. I'm not sure what that means.
So does anyone have an answer to the question, what can you do to make the best measurement possible of that sound?
What are techniques? What could you do?
Okay, so I have an idea. You pull out your telephone and you start the stopwatch function, and you listen to the audio, and you start and you stop on 2 of the sounds. But there might be a better way.
I think that most students would do that, right? They would just go start, stop, start, stop.
Right.
I have a feeling the results would be terrible doing that.
So how do we improve those results?
Right. What could we do?
Anyone?
Okay.
Hey, John, I've got an idea.
What's that?
What if we measure the time it takes for 10 of those pulses to go by?
Okay.
And then divide that amount of time by 10 to get the time for 1 pulse.
Exactly. That's one thing you can do. On our next slide, do we have a list of things that we had listed? I can't remember. Yeah. Okay. So recording multiple pulses at a time. A lot of students will pick up on that. The first time they do it, they'll say, oh, wait, you know what? Let me just let it run for 10, and then we'll divide by 10. Okay. Choice of the timer. You know, suppose that they're using their cell phone. They might want to get a digital stopwatch. And how do you tell which one's better? Well, that's what we have. We have an experiment designed to show that. And also, what about slowing down the video? Could we slow down the video to lengthen the time to reduce the relative error in the measurements?
Okay, so John,
Mm-hmm.
I think the reference to video there is the reference to the
sound.
pulsars that are available on YouTube.
Right.
And this is not one of them.
Oh, that's actually the, one I recorded off YouTube.
Okay, so you just grab the audio off of that.
Right. Exactly.
Okay, so you're talking about slowing down the video on a YouTube video.
Yes, I should have mentioned. There is a web page that has, well, there's a lot of YouTube videos that have these pulsar sounds, and you can play them at quarter speed. So that lengthens the time between the pulses, and it makes it for a more precise measurement.
Okay. So once you get the time for your pulsar, you need to be able to figure out which pulsar it is. So we don't know the correct answer. So what do you do next?
Okay. So what we have is a pulsar catalog that's online. This is compiled by professional astronomers. And you can see here, this is just a screen capture of the actual web page. Go on ahead and go to the next slide. And if you type in, for example, it came the pulsing between that one that we heard is about 0.27 seconds. And if you type in 0.27, you can see the result at the bottom. You won't get anything, because the chances that the pulsar is going to have exactly 0.27 seconds is really, really remote. And therefore, what we want is a range of time, a maximum and minimum, so that it can tell us what pulsars fall in that range of periods. And that's on the next slide. So here we have a range of periods that we type in, and you can see that it has found a number of these pulsars that have periods that fall between those two values. And what this activity teaches is that one, well, what's important here is you can't have too many pulsars, because if you have too many pulsars, that doesn't narrow it down very well. And also, the pulsar that you get, it better be in that list, because if it's not in that list, then that's not good, right? So we're trying to find out which pulsar it is that's making that sound. Go ahead to the next slide.
Okay.
So we created this lab activity, and this is an activity you could do down into probably even like maybe 12, 13 years old. And that is, we usually started off with a light pulse. Actually, isn't this yours, Roger, or did you want me to do it?
No, it's both of us.
Okay. So, go ahead.
Yeah, because I think we're burning up our time, I'm going to make this short. Basically, what this means is that we have a light controlled by an Arduino, and the Blink program in Arduino is a very simple program. Many of us can do it with little help. I took that program and modified it so that the light is on for a specific amount of time. Even the lab instructor does not know how long that is. And then it is off for a random amount of time. And that was really the key here, is that we don't want to be able to condition the students to anticipate when the light will come on. So we have the light off for a random amount of time, and then it's on for an exact amount of time. And even the instructor doesn't know how long that is. So the students are given the task of measuring the amount of time the light is on. Mm-hmm. And then they are this is a wonderful introduction to statistics, because they're making measurements and they're deciding how confident they are in their measurements. And right. Then, and then they're doing the statistics, and here they are.
So this is I'm sorry.
No, go ahead, John.
Okay, so what they really learn out of this is that measuring stuff in the laboratory, measuring properties, is a process. You just can't just simply go in and measure things. And in this case here, they're only measuring the time that it takes for a light to stay on. However, in the first step, I want you to go back one. In the first step, they're going to try to find the best method for measurement. And so they take measurements with different methods they could use, like, for example, a stopwatch versus their iPhone, or maybe the method is letting the thing go for 10 and then dividing by 10, or just measuring between each pulse. But whatever the case, they're going to first find the best method for making the measurement, and that's measured with the standard deviation. So they're lowering the random error as much as they can. And then in step two, they choose that best method, and they use a known pulse duration to find out the bias to calibrate. So if their average measurement is 0.01 seconds too large, they know to subtract that 0.01 from their final. So then once they have the best method and they have calibrated, then they turn their attention to the unknown pulse. And from that, they find the average time, and then they use the standard error to find the confidence intervals. And that confidence intervals is there times that, for example, with the pulsar, that they're going to put into that web page to find out which pulsars is the one making that sound.
Yeah, so this timing the light activity is very similar to the pulsar activity.
Yeah, so it's essentially the same, where we swapped out the light for a pulsar sound. And what does that one do? It really teaches the difference between random error and systematic error. Okay, go ahead, Roger.
All right, so now we come to another experiment we did. And this is one of the first ones, actually, that we collaborated on. It's called Eleusis. It's a card game that's been around since the 1960s, but we put a new twist on it, and we're going to go into breakout rooms soon. And let's see. The idea is to recognize a pattern. So if you understand these cards, you know that the ace is 1. Okay, John.
Never mind my YouTube thing. Sorry, Roger.
No, it's okay. The ace is 1, and then 3, 5, 7, 9. You notice these are all black cards, and what could possibly come next? If you have an idea, drop it in the chat right now.
Yeah, what would you think would be the next? Could be the next card in the sequence.
What might be the next card? The 11 would be, okay, so it goes 9, 10, 11 is Jack.
Okay.
I see some of you thinking, that's good. I like that.
By the way, be sure to note the suit also, clubs, spades, diamonds, hearts.
Okay, yes. So in this game, there are many things that may or may not be relevant. The color of the card, the suit of the card, the number of the card, and anything you can think of.
So we have the Jack of clubs.
Oh, I like that. Yes.
Mm-hmm.
Anyone else?
Okay, 11, which is the Jack. Mm-hmm.
That's also true. Very good. Yes. Okay, maybe you've seen our presentation before. Okay, so we're gonna do.
What we could ask, though, is could the 2 of diamonds be the next one?
Could it?
Anybody
Maybe the pattern is 5 black and 5 red. 5 black and 5 red. Maybe that's the pattern. We don't know. The only way we know is to do an experiment. And that's why introducing this, I do this as the first lab in my college course for future teachers, where we're looking at patterns, and those patterns are easy to recognize. And they're also easy to misinterpret.
Yeah.
Which is the whole idea.
Mm-hmm.
Okay, so here we go. we're going to do this. I'm going to take this YouTube Live and drop it in the chat. I hope everyone can join the YouTube Live there. And we have prepared a sequence of cards for you to do in your breakout rooms. So what we're going to do here is ask you to find the pattern. Okay, so we're going to go to breakout rooms here in a minute, not just yet, but keep in mind, this is a game. This is a game. It's all about using play to illustrate the scientific method.
Yes, and by pattern we mean, is it all clubs increasing by one? Is it alternating red and black? And whatever pattern you think is appropriate, as soon as you see it, go ahead and type it in.
Okay, so unfortunately, there is about a 10-second delay between our Zoom and our YouTube Live.
Oh, no. Okay. Well, we'll do best we can.
Yeah, we'll do the best we can. I'm getting set up here right now. I have our first challenge ready. And if you are viewing the YouTube Live link, which is right there. Oh, did I drop it in the chat yet? Yes, I did.
Mm-hmm.
Apologies. There's a bit of a delay. You just have to wait. And then, okay, so I'm going to go ahead and do that. Join your breakout rooms and see if you can determine. I'm going to breakout rooms here in a minute. But this is a game. This is a game. It's all about using play to illustrate the scientific method.
Yes, and by pattern we mean, is it all clubs increasing by one? Is it alternating red and black? And whatever pattern you think is appropriate, as soon as you see it, go ahead and type it in. It's only good.
Okay, so unfortunately there is about a 10-second delay between our Zoom and our YouTube Live.
Okay. We'll do this.
Yeah, we'll do the best we can. I'm getting set up here right now. I have our first challenge ready. And if you are viewing the YouTube Live link, which is right there. Oh, did I drop it in the chat yet? Yes, I did. My apologies. There's a bit of a delay. Just have to wait. And then, okay, so I'm going to go ahead and do that. Join your breakout
You can't
rooms
see it.
and see if you can determine the pattern. Okay, so this is challenging because you need to see both our breakout room and the YouTube Live. Are you guys able to see the YouTube Live?
Yes.
You got to follow. You got to follow the link in the chat. Okay, so if you're joining the room late, look in the chat for the YouTube Live link click on that and it will open a new window and you will see the two of clubs. You guys see that? I'm sorry. Rathana, I couldn't hear you. No, I have my volume all the way up and I can't hear you. Okay. I'm going to go to the second page. Can someone let me know if you can see the YouTube live? Are you seeing 3 cards? How many cards do you see? Can't hear you. 1, 2, 3. Pull up fingers. So that was a really good experiment. Any pattern emerging? Did you see any pattern? The room I was in had some very shy people. Nobody was saying anything. How about you, John? Sorry, I'm not able to hear you.
Can you hear me?
Yeah, I can hear you. I'm going to shut down the YouTube live stream.
Okay. Well, we found out that the YouTube live stream is a little shaky for doing this kind of thing, I think.
Yes, it is.
Yeah.
But that's a good thing to know. There you go. Okay. So let me share the slides back. And now we're here.
Okay. All right. Roger, why don't you hold up one of the very final?
Okay, so maybe this is not working too well. Okay, you shut up. I'm going to close that window. And let's go back to the main room. Okay. I'll see you all there. Oh, that's
yeah. Well, I think it's just the international distance is just making it rough.
Yeah.
Yeah. We practiced this. We had it really going smoothly, and then we didn't have this. We didn't anticipate this.
Right, here we go. So that was a really good experiment. Shut off that window, John.
Oh.
Did you see any pattern?
Sorry.
There you go. Okay, so it really is a good activity, and I do it with my students who have no mathematical background and who have no um, experience with science at all.
Mhm.
They love playing this game.
Yeah, and it's a competition. So it's very fast paced, and we usually put students in little groups we call research teams, and they watch the pattern unfold. Well, regular elusives, what we call elusives express, the students would take a card that they thought matched the pattern and present it. That's like doing an experiment. And so they would do this experiment, and then the person running the program would tell them whether that card matches the pattern. In this case, the pattern is unfolding in front of them, and it's whoever can guess the pattern first. Well, what happens is, as soon as you guess the pattern, you declare publish, and you tell everybody what you think is the pattern. Okay. Now, another team might come in and say, hey, I think they're right. They can replicate, and they get points for that. The person who publishes gets the points. A person who replicates gets gets a few points, and you continue to play. At some point, though, it may be that the person who first published is wrong. A card comes out that doesn't match their pattern. And all of a sudden, that early publishing is incorrect, and they start losing points for all those points that they were getting become negative. And so at that point, they can retract. And then they can retract their earlier publication, and now they're not bound to losing points anymore. So it's a competition.
John, I think it's worth mentioning that this is a real thing.
Yeah,
That
absolutely.
that very very recently they thought they found life on Venus.
Yes, and it made the news. Now they're looking at those results, and they're starting to become a little bit skeptical. In my opinion, I think they're going to have to retract that paper. So they announced a publication, others replicated, but now more experiments have come out that seems to defy what they were the original publication. I think they're going to have to retract that here at some point.
I agree, and many others do.
So students learn what publication is. They learn that replication's really important, and you get credit for that. And also that there's always the chance that another card will come out that will spoil everything. And that's exactly what happens in science. There a ton of numerous higher order questions can come out of this game. Just to pick up one of them here, is competition healthy in science? This is a competition game. And sometimes some of the students will do certain things to get an edge and stuff. And is that healthy for science? And that generates a lot of discussion among students. Can we ever truly know the secret rule? Suppose we have played 100 cards, and it looks like every one of those 100 cards is even. Does that guarantee that the next card will be even? And the students get to talk about that. But that's just exactly the way it is in science. You never know if the next card that is played is going to destroy what everybody thought was the pattern. And an example of that is quantum physics. Pretty well destroyed classical physics, Newtonian physics around 1900. So perfect example where we get really comfortable with something, and then another experiment comes out and that destroys it. Falsifiability, the fact that one card that you play, when it appears, can destroy what you thought was the pattern. That's also taught really well in this game. Students learn how to distinguish between a law and a model, and a law and a theory. So they learn a lot of scientific vocabulary playing this game as well. A law, once all of the teams have decided that the pattern is the correct one, that becomes a law. However, again, laws can be violated, and there's always the chance that another card comes down, gets displayed, and the whole thing comes apart. And then we have them look at some famous cases of fraud and how that is played out in these games as well. you're the one that's producing these cards, and what if you want it to be a six of diamonds? Well, you can make it look like a six of diamonds. You can play it and fool everybody. And that happens in science. We talk about these famous cases. Okay. By the way, I think that this game could be played probably down to third grade, age 7 or 8. So a lot of the terminology would be a little different. But if you're a primary school teacher and you're looking for a way to teach the scientific method, Elusus Express and Speed Elusus are perfect. They're also great to play on the first day. So if you have a lab that you're trying to figure out what to do, and we have this trouble, we get everybody in there, we don't know what to do. We go over the syllabus and we talk about the rules and all that. But this game is perfect for day one. It's a great icebreaker. It's a lot of fun, and they learn a lot. Okay, Roger, I think we're headed for, okay. All right, so what we have here is another activity that we'd like you to talk about. And this is a challenge. So you got to think that you're the boss of a company that manufactures fireworks. Now, this is a new design. So somebody come up with a new design of a firework, and you have to manufacture these fireworks, and a client wants to buy them from you, and he'll pay $10. I'm not certain what currency you use in Cambodia, but $10 each. He wants to buy 10,000 of them. However, it costs you $5 to make each one. So you're getting a 100% profit. There's one small problem. If more than 10% of the fireworks are defective, they'll cancel all your contracts. They're going to get very angry. They might even send the ones that you gave them back and get a refund. So you need to test your fireworks. But the only way to test them is to explode them. Now, you can test every one of them you want, but you're not going to have anything to sell, right? The great news is all of our fireworks are perfectly good. The bad news is we don't have any to sell because we exploded them to find out, right? So that's no good. So the question is if you're the boss of this company, and given all this, what would you do to maximize the profitability? What kind of decisions would you have to make? What type of questions would you have to ask? So this is a very real world problem. And an example came out of the news where they had a supercar company in Britain that was charging $250,000 per car, extremely expensive, but they only make 20 of them. How many of them can they crash? All of them? 2? So that was an example where the company had to make some hard decisions about how many of their product they could destroy in making their measurements. So should we go into little breakout rooms for maybe a couple of minutes? And I think, Roger, this will be the last activity. I think the momentum one is something we can skip.
I think I agree. Okay. And I stand by for the moderators to give us breakout rooms.
Right. What kind of questions can you ask? What would you need to know? I think I'll stay here, Roger, not join the breakout room. I think our presence kind of changed the environment a little. Yeah, this is our last activity. Okay, you're on mute. Okay, why don't you go ahead and just give them one more minute, and then we'll close the breakout rooms. So we can go ahead and close them now if you want to give them one more minute. Sean Hing, I think you're on mute. I don't know if you wanted to speak to us. Okay, we should be getting back now. Okay, are we back?
Yeah, we're back, but I see somebody who I wanted to talk to some more.
Who's
You know
that?
who you are.
Who's that?
iPhone, right over there. Hi, iPhone.
Okay. All right, Roger, why don't you post that thing up again? Let's get her finished up.
Yeah, okay. I think we're running out of time.
Yeah, I'm just going to, let me just talk about that first slide, and then we'll be done.
This one?
No, the next one. Well, there were some things that we could have thought about. How many fireworks do you decide to sample? How do you select them? Do you just grab them? Is there a process? And how do you plan? How did you decide whether if 10% of your entire shipment was going to be defective or not? So those are things you have to think about. Go on to the next one. Okay, so in a nutshell, long story short, we turned the physics lab into a manufacturing facility. Students rolled ball bearings out of clay, and they had a little target one to try to mimic, and they would sample. They were supposed to make 40 of them, but they were only allowed to collect 6 of them at a time. So they would take 6, roll them, perform statistical measurements, then decide what they could do to make the bearings better. And then they would collect 6 more, roll them, make measurements. And this is all designed to teach the plan, do, check, act, continuous improvement cycle. So this is a lab designed to teach students how to improve the quality of their products. And it's a process. And it's heavy duty industrial engineering. It's the Six Sigma quality control process used by Motorola and Toyota and all these big time manufacturers. But it could be done probably in secondary school as well. So in a nutshell, that's what we designed with this experiment. And I really wish we had more time to cover it. And I think at this point, Roger, do you want to turn over some questions and answers?
I think that's a good idea.
Okay.
We only have about 10 minutes left.
Right.
So I think it's a very good time to open up to Q&A.
Sure. So if anybody has any questions, by all means, turn on your microphone or type them in the chat window.
So yeah, thank you so much for your fantastic presentation. So because it is time limitation, so we open the question and answer sections for everybody. So I would like to remind everybody that if you have any questions, please kindly drop your question in the box chats here.
So since you said we could ask live, I just thought I would ask about a curriculum. I know that you said that you can mention that you could do these activities even in third grade for the card game. And
Right.
is there something written up that would that we could give to teachers or have translated that kind of gives them an idea, since they've never seen this type of thing before, of what to do?
Sure. First of all, there are already papers published. We published one on this. If you email me, and I just put my email address in the chat window, email me and I will send you whatever you would like.
Okay. Thank you.
And that's true for everyone. Anybody would like more information on the Elucis card game and how to play it, email me and I will certainly get on, and I'm willing to Zoom with you anytime to help you get the thing implemented.
And me too.
Absolutely. We love it.
Mm-hmm.
We really think that this is a great activity for kids. By the way, I should also, go ahead.
And what about the ball bearing thing? That's a great thing, because clay is in we have clay here. We have
Sure.
different ways to do that. And that
Okay.
would be a great activity to teach so many things related to science.
Right, and that was published in the American Journal of Physics. We have an actual lab manual written up on it. And again, if you email me, I will absolutely do everything to help you get started up on that. That is probably our coolest experiment we ever did. And,
John, just a reminder that most people don't have access to AJP without paying a fee.
Right,
So
but I can
if they
send them the article.
If they contact us directly, we can send it to them. Yeah.
Yeah, we'll send you the article.
Okay.
Yeah, and that's also an experiment you can do early on because it doesn't require any physics background. It's strictly a statistics analysis project, but it's really heavy duty industrial strength quality control, the stuff they do in the actual big companies. It's just that clay, we can't do 6 sigma, we have to do 1.5 sigma because there's no way they could roll bearings that precisely. Any other questions?
What about other things that can be done through distance learning or inexpensive labs? Like in Cambodia, there's a real issue about equipment. And also there's an issue about things that are quantifiable. So many things here are just qualitative. And
Right.
I'm just wondering, what are some strategies to increase the clay one's great because you measure and it doesn't take a lot of expensive equipment, but are there other recommendations that you would give for developing countries for
Sure.
labs?
Oh, yes. Oh, yes, definitely.
Absolutely.
One of my first encounters with a reference in terms of teaching physics in other countries was a wonderful book that came from UNESCO. And it had lots of ways of doing science with native materials. So I don't know if that's still available, but you might look into the UNESCO library And sorry, yes, go ahead.
Oh, can I go ahead and mention also that
Yes.
our lab, we went virtual this current semester. All of our labs are done online, and we have some where students can perform these experiments with just ordinary household materials. And go ahead.
John, can I make a comment here?
Sure.
There are free resources online, mostly at PhET, P-H-E-T, which is a online simulation library that is completely free. Yeah, sorry. And if you need any help with that, contact me directly. I have many laboratories already written up to use just the free resources.
You know, Roger, I wouldn't actually mind partnering up to kind of help get things rolling there wherever she is. Why don't we converse sometime after the conference and let's help.
Agreed.
So yeah, please contact us. We're excited about this. This is great.
We actually have a project with 2 different schools here. One's a part of a group of 10 and the other's a private school to try and use the Raspberry Pi to collect data. And so I've got Raspberry Pi from the Internet in a Box Foundation, and I'm now trying to load it with inquiry-based things and content that we can distribute to rural schools. And so it sounds like what you have is a great match, because we could translate it into Khmer, and then it would be things that could be used that would complement the UNESCO stuff and might move it forward in terms of it being a bit more higher order thinking skills. Yeah.
I agree. And if you're working with Raspberry Pi, talk to me privately, please.
Okay.
Yeah. And we've done some recent work with an online Python compiler for doing some simple radiation experiments, for example. I don't know what grade level you're referring to back there, but and this goes for anyone. If anybody would like us to help, maybe partner up and provide some support for you, by all means, just email us. We're more than happy to help. We're really eager.
With the Raspberry Pi, there's a lot of different ways that you can do the probes. And so I've got the vernier probes. I've got a whole set, but they're too expensive for Cambodia, but I love them. And I'm using those through a STEM lending library now. So schools can rent them out, or, for free, they can borrow them. But there's a lot of sensors that you can attach to the Raspberry Pi. Do you have a list of ones that, my shopping list, so I could order sets for schools? I'm just wondering, and I know that the mobile phone can do some things, but if I'm trying to use the Mathematica or use different types of programs in Python on the Raspberry Pi to do quantitative analysis, I'm not quite sure where to go to, or how to put together a package for the sensors.
In your emails, be sure to include that and we'll get on it.
Okay.
Well, one more thing I would like to mention, because we shifted our focus towards error analysis, error is good. We don't necessarily want great equipment, because the whole point of our labs is to investigate error. And so if you are at a school that doesn't have a lot of really good equipment, great, because that actually is a learning opportunity. And we actually, in our labs, we push aside our really good equipment and we bring out the really bad stuff from years past, because it's actually better learning experience for the students. Good deal. Looks like we're just about out of time. Yeah, be sure to email us.
Okay. Great talk. Thank you so much.
Thank you
so much.
We appreciate it.
Thank you for the
Thank you.
feedback.
So we have one last question
Sure.
from Q Sochit. So the question is, would you share about the structure of staff responsible for?
Okay, Roger, I think that's for you.
Okay, so I'm not sure I understand the question. A staff responsible for what? because
So
John is
please,
faculty and I am staff, and I take care of all the nuts and bolts, and he does all the high level theory. So,
Although I
we-
will say, Roger, you are really a hell of a teacher too. So
well, thank you for that. I do my best.
So I guess we're a little unclear as to what you mean by the structure of the staff. You know, I'm pretty much the one that, let's say, handles the in-class unfolding of this, and Roger is on the equipment side, making sure that we have the stuff necessary to perform it. But I'm not quite sure I understand.
So, excuse me. So if
Okay.
there are more questions and if they would like to ask you later on directly, so would you mind answers all those questions, sir?
I think we would be very happy to answer all questions from email.
Sure.
Yeah, thank you so much for your kindness. So the rest question, if they have, yeah, we would copy and send those questions to you directly. And we thank you so much for joining us today and sharing such a very interesting and meaningful topics for all the participants. And we hope that
Thank you so much for including us.
thank
Yes,
you,
we
thank you.
appreciate
And
it.
we hope that we can see you next time and you will share like a wonderful different topics to everybody, to all the participants around the world too.
Yeah, and
So
we
we
want you
would
to
like
YouTube
to
live.
say,
We
we would like
love
to
to
say
be-
that this session is going to the end. However, we will have plenary sessions in Group A. So we will drop the link below in the chat
good.
box. So yeah, all the speakers and participants can click on the links that we share in the box chats, and we will listen the other speakers, yeah, from around the world in the plenary session. So we hope that everybody join us the next session. So thank you so much for
Thank you.
today's.
Take care.
Thank you. Goodbye.